Introduction to the Natural Science of Electricity. This is Lecture 2 of Physics 101. Let's begin with some definitions. Electric charge. The physical property of matter that causes it to experience a force when placed in an electromagnetic field. Like how mass is a physical property of matter that causes it to experience a force when placed in a gravitational field. Charge is quantized. In physics, a quanta is the minimum amount of any physical entity involved in an interaction. All isolatable particles have charges that are integer multiples of E, which is the smallest charge which can exist freely. The proton has a charge of plus E, and the electron has a charge of negative E. As an example, here is an oxygen atom. Atoms are composed of protons and neutrons in the center, and electrons which orbit the protons and neutrons. Oxygen has 8 protons, 8 neutrons, and 8 electrons. The protons all have a value of plus E. The neutrons have a value of 0, and the electrons have a negative E. The positive electrons and the negative electrons balance each other out. The law of electric charges. The law of electric charges states that like charges repel and opposite charges attract. If we were to take these charges and suspend them from ropes, we can get something that looks like this. All of the like charges repel, so the positive and positive repel, negative and negative repel, and the positive and negative attract. What is static electricity? Static electricity is when electric charge builds up on the surface of an insulator. The charge that has built up cannot easily flow away from the insulator, which is why it is called static electricity. The common similarity between the 3 ways to statically charge an object is to get electrons to transfer from one material to another. Electrons have negative charge all of the time, so when you move them from one surface to another, the object that the electrons are leaving gains a positive charge because it has lost the negative electrons. The object that gains electrons gets a negative charge because it has gained the negative electrons. Creating a static charge. Static means not moving, so if we want to create a static charge, we need to use an insulator because they don't let electrons move around. If we rub the insulator, in this case a rubber rod, with a less insulating material like fur, then the electrons will move from the fur to the rod, like such. Charge by friction. Charging by friction occurs when negatively charged particles called electrons are wiped from one object to another. Example: suppose you touch an uncharged piece of rubber with a negatively charged cat. Electrons from the cat will move to the rubber rod. The rubber gains electrons and becomes negatively charged. Charge by conduction. Charging by conduction happens when electrons move from one object to another through direct contact, touching. Example: suppose you touch a charged piece of rubber with an uncharged glass rod. Electrons from the rubber will move to the glass rod. The glass rod gains the electrons and becomes negatively charged, and the rubber rod will become less negatively charged. Charge by induction. Charging by induction happens when charges in an uncharged object are rearranged without direct contact with a charged object. Example: if you charge up a rubber rod through friction and place it near a neutrally charged balloon, the charges of the balloon will be rearranged and the balloon will be attracted to the rubber rod. Conservation of charge. Charge conservation is the principle that the total electric charge in an isolated system never changes. The net quantity of electric charge, the amount of positive charge minus the amount of negative charge in the universe, is always conserved. An example from chemistry is the sodium atom and the chlorine atom. The sodium atom has an extra electron attached to it. This electron is given to the chlorine atom, making the sodium atom a sodium ion and making the chlorine atom a chlorine ion. This gives the sodium ion a positive charge and the chlorine a negative charge. But the whole setup used to be neutral, so a sodium and chlorine come together and become neutrally sodium chloride. Conductors and insulators. An electric conductor is a material in which charges can move easily. Most metals are good conductors because some of their electrons are free to move. Conductors are used to make wires. For example, a lamp cord has metal wires and metal prongs. Copper, aluminum, and mercury are good conductors. An electric insulator is a material in which charges cannot move easily. Insulators do not conduct charges very well because their electrons cannot flow freely. The electrons are tightly held in the atoms of the insulator. The insulating material in a lamp cord stops charges from leaving the wire and protects you from an electric shock. Plastic, rubber, wood, and ceramic are good insulators. Electric discharge. The loss of static electricity as charges move off an object is called electric discharge. Sometimes electric discharge happens quickly. This is because the charge builds up enough energy to cross a gap. A bolt of energy can discharge the built-up charge. Example: lightning is a bolt of energy that had enough energy to cross the gap from the clouds to the ground. Or if you drag your feet on the carpet, you can build up enough energy to make a bolt of energy when you touch another person or anything metal. Sometimes electric discharge happens slowly. Example: if you don't attempt to remove clothing that is statically clinging to another piece of clothing, over time the charge will be lost to the air and environment and will discharge enough to fall off without aid. Charge by chemical energy. Thanks to Alestra Volta's invention, the Voltaic pile, in 1799, scientists finally had a reliable, constant source of electricity. Rather than dealing with static discharging lightning bolts, now electricity is able to flow like a river in a closed loop. Part 1. The flow of charged particles. Some historic background. Chemical reactions in cells constantly produce free electrons, which accumulate on the negative electrode. Electrons move from the negative electrode, which we say are repelled, through the conductor loop to the positive electrode, which we say the electrons are attracted to the positive electrode. Volta's battery was composed of copper and zinc. The higher the electronegativity, the more an atom attracts electrons. Copper has a 1.9, zinc has a 1.65. So the electrons from the zinc go to the copper. This makes the zinc plate positive and the copper plate negative. This creates an electric field between the two plates. The way we draw these diagrams is that current goes from the positive to the negative. So the electric field goes from the zinc to the copper. If we were to attach a light bulb to this picture, we could then see what happens when we attach the wires to the metals. Electrons move in the opposite direction of the current. So the electrons would flow from the zinc to the copper, passing the light bulb. But once all of the electrons have passed, the light bulb turns off. This is because there is nothing in between these two plates. Volta's battery used brine-soaked cloth between these two plates. The brine-soaked cloth has sodium and chlorine ions floating in it, as well as water. This water breaks down to H plus and OH minus. The zinc breaks down from zinc to zinc plus 2. The 2 electrons from each zinc travel through the wire and attach to a hydrogen. Over time, the zinc runs out of energy, and the battery dies. Historic background. Hans Christian Ørsted in 1820 observed that the needle in a compass used to detect the magnetic field of Earth was deflected by his current experiments with his Volta battery. Ørsted found for a straight current-carrying conductor, a current-carrying wire creates a magnetic field of force which encircles the wire. The magnetic field lines of force lie in a plane perpendicular to the conductor, i.e. at right angles, 90 degrees, to each other. The change in the direction of flow of current will also change the direction of the magnetic field lines of force. The magnetic field strength is directly proportional to the current density. The magnetic field exists around the wire until the flow of current is abandoned. André-Marie Ampère in 1820 showed that 2 parallel wires carrying electric currents attract or repel each other depending on whether the current flows in the same or opposite directions, respectively. This laid the foundations of electrodynamics. Quickly following this discovery, Ampère discovered that if a wire is coiled like a cylinder, called a solenoid, it starts to act like a bar magnet. Ampère showed that the magnetic field can only exist in a closed loop of electrical current, and that the magnetic force depends on the intensity of current. To prove this, Ampère created many different experiments to demonstrate this relationship between electricity and magnetism, and coined the term electromagnetism. One example of Ampère's experiment is shown here. A battery of copper and zinc is placed in a salty bath. The apparatus suspends a metal bar hanging loosely from a wire. 2 mercury cups, which are attached to the battery, are also attached to another metal bar. When electricity is flowing through this closed loop, a magnetic field is created, and the bar on the wire is pushed away. When the loop is no longer closed, the magnetic field disappears, and the bar goes back to normal. If you then add more power to the battery by adding more plates, and then reclose the loop, the magnetic field grows stronger. The invention of the ammeter allowed scientists to be able to measure the current in a circuit by measuring the deflection caused by a created magnetic field. Definition: electric current. Current is a measure of the rate at which electric charges move past a given point in a conductor per unit time. This can be written like this. 1 unit of intensity of current is equal to 1 unit of electric charge over 1 unit of time, usually in seconds. This can be simplified to I equals Q over T, where I is the intensity of current, Q is the electric charge, and T is the time in seconds. The measurement unit for current is in amperes, which is denoted with an A or an amp or amps. The measurement unit for charge is in coulombs, which is a capital C. And the measurement unit for time is in seconds, denoted with a small s. So we can also write the I equals Q over T as 1 amp equals 1 coulomb per 1 second. This formula can be written in the form of a triangle, such as I equals Q over T, or Q equals I times T, or T equals Q over I. Measuring current. To measure the current, we use an instrument called an ammeter. Ammeters only record the number of electrons passing through the conductor. 1 coulomb, 1 C, is equivalent to 6.25 times 10 to the 18 electrons. Using the current equation. Remember to convert time into seconds to use the equation. So we have I equals Q over T. One example. If the question asks how many charges pass through an appliance over a time period of 20 minutes, you need to turn 20 minutes into seconds. 20 minutes times 60 seconds per minute equals 1200 seconds. Two hours would be 2 hours times 60 minutes per hour times 60 seconds per minute, which would equal 7200 seconds. To help solve problems, you can use the guess method for problem solving. G stands for what is given. U stands for the unknown. E is the equation that you will use. S is the substitution that you need to do. And the other S is the solution. Let's give an example. Example 1. How much time does it take for 80 coulombs to pass through a light bulb that draws on 0.4 amperes? Given. We know the current, I, is 0.4 amps, and the charge, Q, is equal to 80 coulombs. The unknown, then, would be the amount of time, T. The equation, then, is T equals Q over I. So we substitute in the given. T equals 80 coulombs over 0.4 amps. The solution then, T equals 80 coulombs over 0.4 amps, would get us 200 coulombs per amp, which is equal to 200 seconds. Converting this back into minutes, we get about 3.33 minutes. Therefore, it takes about 3 minutes and 19.8 seconds for 80 coulombs, or 5 times 10 to the 20 electrons, to pass through a light bulb that only uses 0.4 coulombs per second. Example 2. How many electric charges pass through an appliance that draws 40 amps over 30 minutes? Given. Current, I, equals 40 amps. Time, T, equals 30 minutes. Unknown, then, would be the charge, Q. The equation, Q equals I times T. Substitution, Q equals 40 amps times 30 minutes. But we need to convert that. So Q equals 40 amps times 1800 seconds. Solution, 40 amps times 1800 seconds gives us 72,000 coulombs. Therefore, we can say 72,000 coulombs of charge, or 4.5 times 10 to the 23 electrons pass through a 40 amp appliance in 30 minutes. Part 2. The voltage of a current. Historic background. In 1687, Isaac Newton published his thesis, Mathematical Principles of Natural Philosophy. Among a great many other scientific observations, Newton describes the three laws of motion in a mathematical framework, famously known as the three laws of motion. This is what gets us a mathematical formula for what force is. In 1698, Thomas Savery, a military engineer, invented a rudimentary steam pump. This pump was used to do work, to drain mines of water, but it couldn't lift water from deep mines. The mathematical formulation of work is work equals force times distance. In 1712, Thomas Newcomb invented the first commercially successful engine, which used pistons and cylinders, and was invented to be a replacement for Savery's pump for mining. For the next 60 years, engines were driven by steam or by horses. In 1774, James Watt invented a new steam engine and marketed a deal with people who were buying the Newcomb engines. However, those that used horses needed a new marketing strategy to sell to. So Watt coined the unit horsepower. Power is equal to work per time. In Watt's unit, 1 horsepower is equal to 33,000 foot-pounds per minute. In 1840, brewer Benjamin Joule considered replacing the brewery's steam engine with a newly created electric motor, but found that burning a pound of coal in his steam engine produced 5 times more work than the electrical engine he had. He called it duty. 1 duty is equal to the ability to raise 1 pound by 1 foot, the foot-pound. A joule is equal to the energy transferred to, or the work done on, an object when a force of 1 Newton acts on that object in the direction of the force's motion through a distance of 1 meter. 1 joule equals 1 Newton times 1 meter. Therefore, joule is work. Work equals force times distance. In 1882, C. William Simmons proposed the unit name watt for the power conveyed by a current of an ampere through the difference of potential of a volt. 1 watt equals 1 volt times 1 amp. This gets us power, as a volt is a work per charge, and an amp is a charge per time. So, 1 watt's power is equal to the work per charge times the charge per time. This can best be seen in an illustration. The work done by the horse is moving 550 pounds 1 foot. The power done by the horse is moving 550 pounds 1 foot in 1 second. Now that we have a 550-pound box suspended 1 foot in the air, we can see that gravity is going to force that box back down towards the earth. We know that if we cut the line holding the box, that box will fall down and be kinetic. So as long as we don't cut the line, the box will stay in the air with the potential to fall down and become kinetic. In this way, we can see that the work done to lift an object from a position of 0 potential energy to greater than 0 potential energy, then work done is equal to the negative change in potential. Work equals negative change in potential energy. This can be written W equals negative change of U. U is the common notation for potential energy. Voltage, V, is a form of potential energy. Definition. Potential energy. Potential energy is the energy stored by an object because of its position relative to other objects, stresses within itself, its electrical charge, or other factors. Voltage is the difference in electrical potential between 2 points, which, in a static electric field, is defined as the work needed per unit charge to move a test charge between 2 points. work per unit charge is expressed as joules per coulomb. So this can be written as 1 volt equals 1 joule per 1 coulomb, where V is the voltage, J is the work, C is the charge. This can also be expanded as 1 newton times 1 meter per 1 coulomb, where N is a newton of force and M is the meter of distance. Voltage. Voltage can be simplified into the idea that 2 points in a wire can have different potential energies, especially if the current is running through an appliance or resistor, which is converting some of that energy into light and heat. So we can write a change in voltage as a change in energy per charge. This gives us a formula like the difference in potential, delta V, is equal to the final voltage minus the initial voltage, which is the change in potential divided by the charge. The final voltage can be written as the final energy divided by the charge. The initial voltage is equal to the initial energy divided by the charge. V is voltage, E is the energy in joules, and Q is the charge in coulombs. So the 1 volt per 1 joule over 1 coulomb becomes V equals E over Q, which is the exact same thing as 1 volt equals 1 joule per 1 coulomb. Voltage, electric potential difference, is a measure of difference in energy per unit charge between 2 points along a conductor. V equals E over Q. V is the potential difference, E is energy, and Q is the electric charge. The measurement unit for voltage is in volts, V. The measurement unit for energy is in joules, J. And the measurement unit for charge is in coulombs, C. 1V equals 1J over 1C. This can be written in the same triangle form as the current equation, where we can see that V equals E over Q, E equals V times Q, and Q equals E over V. Measuring voltage. To measure the voltage, we use an instrument called a voltmeter. A voltmeter is an instrument used for measuring electrical potential difference between 2 points of an electric circuit, and it is connected in parallel. You can see in the diagram there that the voltmeter is on either side of that light bulb. It usually has a high resistance, so that it takes a negligible current from the circuit. 1 volt, 1V, equals 1 joule per 1 coulomb. So this is equal to 1 joule per 6.25 times 10 to the 18 electrons. Let's do a physics example. Example 1. A battery converts 1200 joules of chemical energy into electrical energy. This places 15 coulombs of negative charge at the negative terminal. What is the potential difference between the negative and positive terminals of the battery? Given. We have the energy E, which is equal to 1200 joules, and the charge Q, which is equal to 15 coulombs. Unknown. What we don't know is the voltage, the potential difference. But we do know the equation. V equals E over Q. Substituting this in, we can see that the potential difference will be 1200 joules divided by 15 coulombs. So our solution. V equals 1200 joules per 15 coulombs. So this gets us the potential difference is 80 joules per coulomb, or 80 volts. So we can write this as the potential difference between the negative and positive terminals of the battery is 80 volts. Example 2. If a gas generator produces 85 volts with a charge of 12 coulombs at the negative terminal, how many joules of energy are produced? Given. We are given the voltage V as 85 volts and the charge Q as 12 coulombs. So then our unknown would be the energy E. equation, we know that E equals V over Q. So we substitute this in, and we get E equals 85 volts over 12 coulombs. So our solution, E equals 85 volts over 12 coulombs, so E equals 7.0833 repeating volts per coulomb, or 7.0833 repeating joules. So we can say that about 7 joules of energy are produced when a gas generator produces 85 volts with a 12 coulomb charge. Part 3. The resistance to a current. Some more historic background. Georg Simon Ohm was a German physicist in the early 1800s, credited with the first resistance measurements. However, these measurements were relative measurements, as the unit of resistance did not yet exist. Ohm constructed a measuring device that used a torsion balance to measure the magnetic field generated by the current in a wire, which was easily replaceable with other wires of different sizes, lengths, and materials. Ohm's first measuring device used a Voltaic pile, but the pile did not last long enough to get the type of evidence required to prove his hypothesis that current was related to the voltage by some contiguous action, as opposed to the action at a distance action like that of static and gravity. Action at a distance is a topic we will come back to later in the series. So here's Ohm's setup. Ohm used a torsion balance that was similar to Coulomb's, which was used to discover the fundamental laws of electricity. Ohm had multiple different cables of different sizes and lengths, which he would then take one of them and plug them into these two mercury cups. This would cause the needle inside the chamber to twist. Just like Coulomb, the twisting of the wire is what is being measured. But this setup didn't work very well because of the Voltaic pile that's sitting in the corner there. Ohm's functional measuring device used the Seebeck effect to generate a steady current that lasted longer than the pile, as well as being able to conduct current through longer or thicker wires. Energy, whether that is in the form of heat or electrical potential difference, can drive the contiguous action of the circuit, as we found when we wrote V equals E over Q. The Seebeck effect uses hot and cold to generate electricity. The hot boiling side has fast-moving atoms and molecules made of charged particles, and the other side is the cold ice water that has slow-moving atoms and molecules made of charged particles. The energetic, fast-moving particles transfer the extra energy to the particles with less energy. Low-energy, slow-moving particles cannot lose any energy as they are at a minimum. This energy difference produces a flow of charge by transmitting energy from high to low. Ohm's new instrument looked more like this. There was a boiling water, about 100 degrees Celsius, attached to ice water, about 0 degrees Celsius. The difference between the two temperatures creates an electric circuit. So, when Ohm attaches the wire, he gets the effect that he was looking for. Ohm's law is the most important early quantitative description of the physics of electricity. When Ohm published his first work in 1827, called The Galvanic Circuit Investigated Mathematically, he stated mathematics possessed in this way as a new field of physics from which it had hitherto remained almost totally excluded. The main merit of mathematical analysis is that it calls forth, by its never vacuating expressions, a generality of ideas, which continually demands renewed experiments, and thus leads to a more profound knowledge of nature. Ohm's critics, to whom held the Hegelian scientific philosophy of the time, asserted that experiments need not be performed to develop an understanding of nature, because nature is so well ordered, and that scientific truths may be deduced through reasoning alone. Because of this philosophic view, his critics called his work a web of naked fancies. The German Minister of Education proclaimed that a professor who preached such heresies was unworthy to teach science. Definition: electrical resistance. The electrical resistance of an object is a measure of its opposition to the flow of electric current. If a current in a wire encounters resistance, the electric potential difference decreases. 1 unit of resistance is equal to 1 unit of change in potential over 1 unit of intensity of current. This can be written R equals V over I. R is usually represented with the omega symbol. Omega is the resistance in ohms. V is the voltage in volts. I is the intensity of current in amps. So we can write this as 1 ohm equals 1 volt per 1 amp. Or 1 ohm is equal to 1 joule per 1 coulomb times 1 second per 1 coulomb, which can be reduced down to 1 ohm is equal to 1 joule second over 1 coulomb squared. Measuring resistance. To measure resistance, we use an instrument called an ohm meter. Ohm meters are an electronic device used to measure electrical resistance of a circuit element. An ohm meter is typically not attached to the circuit while it is in use. Instead, an ohm meter is used separately to measure just the elements in the wire. In order to figure out how to write the equation, we can turn back to the triangle. We would know then that R is equal to V over I, and that V is equal to R times I, and that I is equal to V over R. Let's do some examples. Example 1. An electric stove is connected to a 240 volt outlet. If the current flowing through the stove is 20 amps, what is the resistance of the heating element? Given, the current I is equal to 20 amps. The voltage V is equal to 240 volts. Our unknown then is resistance in ohms. Given this, we know the equation. R equals V over I. If we do a substitution then, we know that R equals 240 volts over 20 amps. So our solution would give us 240 volts over 20 amps. R is equal to 12 ohms. So we can say the resistance of the heating element on the 20 amp stove is 12 ohms when connected to a 240 volt outlet. Example 2. A 30 volt battery creates a current through a 15 ohm resistor. How much current is created? The given voltage is 30 volts. The resistance in ohms is 15 ohms. Our unknown then is the current in I. Therefore, our equation would have to be I equals V over R. So we substitute this in, we get I equals 30 volts over 15 ohms. Our solution then will be I equals 30 volts over 15 ohms. Therefore, I equals 2 volt per ohm, or 2 amps. So we can say the intensity of current is 2 amps when a 30 volt battery is connected to a 15 ohm resistor. Let's draw this to a conclusion. Let's conclude by integrating this whole thing into a functional circuit. We have a battery, an amp meter. The amp meter goes to a resistor, which goes to the source, which is a light bulb. And then we can have a voltmeter that's checking the potential difference between the initial side of the battery and the final side of the battery. We can draw this in a more legitimate schematic. To make a light bulb shine, we first need a source of energy. The source can be created from anything that increases or has a potential energy difference. Nature abhors a vacuum, and that includes potentials and gradients. So potential energy is naturally converted into kinetic energy as soon as it is possible to do so. And that will occur when we attach a wire to the battery. This non-electrical source potential energy difference produces the electrical action, which carries the current around the circuit, which is called the electromotive force, or EMF, sometimes denoted with the symbol capital epsilon. Although the electrons go from negative to positive, we say that the current goes from positive to negative. The potential difference, or the EMF, can be measured with a voltmeter, which measures the charge on one side of the source compared to the other side of the source. The quantitative measure of potential difference is given the unit concept volts. In this case, we're going to say that the battery has 12 volts of potential difference. The current can be measured with an ammeter, which measures the number of charges that pass through it over a given time. The unit concept given to this quantitative measure is called amps. In this case, we're going to say 4 amps. The current flow of electricity in a circuit causes the wire and appliances to heat up and potentially start on fire. So the flow of electricity needs to be slowed down in order to make use of the electrical phenomena. A resistor is a material which is designed to slow the current, which is done by being made of a material which resists electricity. Resistance is the measure of charge a resistor resists, which is given the unit concept ohms. In a series circuit like the one below, it doesn't matter where the resistor is located, as the energy cannot flow at all without being a complete circuit, which means the resistor will act to slow down the flow no matter which direction the current flows or in which order it receives it. In this case, we're going to say the resistance is 3 ohms. The energy that is required to make a light bulb shine is called power, which is the amount of work done per a given amount of time. The work available to the light bulb is given by the work done on the charges, which is generated by the potential difference of the source of energy. The power consumed by the load, the light bulb, is measured in joules per second and is given the quantitative unit concept watts. In this case, mathematically, we would have 48 watts. And that concludes Lecture 2. Don't forget to like, subscribe, ring the little bell, and if you're so inclined, go to our Patreon and support us at patreon.com/youexist.